Alright, and so here, this was the basic form of a departure function, okay, for enthalpy. In this last video, I just want to make some, kind of departing comments about departure functions. Alright, and so, at least in the literature, I'll say, you'll also hear departure functions also referred to as residual functions. It's a different name, but these are the same exact thing, okay? And in general, I showed you, how we derive the departure function for enthalpy. But if you wanted to, you could derive a departure function for really any intensive property. Okay? And so the general form would be the same, where let's say m is just some arbitrary intensive property, and if you take your actual value minus the ideal gas version of that value, the departure function would be the difference between the two. Okay? Alright, and so to demonstrate this, I'll just say, at least, that you can derive these for internal energy and entropy. I won't go through the full derivation, but essentially, for internal energy, your departure function would look like this. And for entropy, your departure function would look like this. Where this z here, this is the same z that we talked about in the virial equation of state, where z is just p molar volume over RT. Okay, that's all it is. All right, and so the departure functions that I wrote out here, and I wrote for enthalpy, these are all taking the integral with respect to pressure, and the derivative that you would take on the inside is like volume with respect to temperature. Okay, and so this form is fine to use if you're using an equation of state where the volume, you could rearrange for volume explicitly, right? Where you could rearrange the equation so that it's like volume is equal to stuff on the right hand side. Okay, but a lot of times the equation of state that you're dealing with, you can't really rearrange the equation so that it's explicit for volume, right? So for instance, if you had the van der Waals equation, you can't really rearrange that equation to just have volume on the left-hand side and everything else on the right-hand side. Okay? And so it turns out that it's a bit more convenient to derive departure functions where instead of pressure being integrated, instead you're integrating volume. And then you would be taking a partial derivative of pressure with respect to temperature instead. Right? And so if you did this way, your departure functions would look like this, where now the bounds of the integral aren't from zero pressure to pi, but now you're integrating from infinite volume to vi, right? Because ideal gases have infinite volume. Or, yeah, the molar volume is infinite. Okay, in any case, so T this is the form of the internal energy departure function. this is the form of the enthalpy departure function in terms of volume. And then here is the entropy in terms of volume. Okay. All right. Yep. So these are the different forms of departure functions, and we'll go through examples that demonstrate, the utility of this sort of departure function approach, and how it's a bit, it can be easier to use this departure function approach in contrast to just directly using the calculus of thermodynamics. The last thing I want to mention is, I wrote departure functions for internal energy, enthalpy, and entropy. But once again, you could write departure functions for any sort of intensive property. For example, we could also derive a departure function for the Gibbs energy. And the way to do this, rather than using the calculus of thermodynamics, what we could instead do is just invoke the fundamental equation for a Gibbs energy, which is just H minus Ts. Okay? And so if we take our H and our S from here, what we get is this. Okay? All right, so this is the Gibbs energy departure function. And the reason I'm introducing this now is because in later chapters, we're going to talk about this thing called fugacity, where, and we'll talk about it more later, but you could kind of think of this as a non-ideal version of pressure. So fugacity, which is abbreviated as F, is just equal to the actual pressure of your system times the exponential of your Gibbs departure function over RT. Right? So essentially the form here is taking your actual pressure and then multiplying it by a term that accounts for non-idealities. This is something we will discuss in the future.